Good morning.
Yeah, I think that Mr. Gerald is not here.
The we don't have the chair. Hello? Can you hear me?
Yeah, I can hear you. Hello. Hi.
Can you hear me? I need some help here. I need some feedback because we're having technical issues and I want to know if I am heard.
Yeah, I can hear you. I can hear you. Sorry, I
Okay,
didn't understand.
Yes.
okay. I'm sorry, but we have some issues with the sound. So,
Okay.
um, you both presenters?
I'm present. I don't know the other one.
Yes, also I.
Okay,
Okay.
so we don't have Mr. Carpentieri for chairing the session, so I will chair the session, so we can start. Okay.
Okay, for me it's okay.
Okay.
Okay. Um, I don't know your presentations. I'm just watching now. Who is first according to the
Uh,
program?
I'm looking.
I think Francesco, you are third.
Yeah, I'm the first. Yeah.
You are the third, and Sophia.
The last.
You are the last.
Yes.
Okay, so we can start with Francesco.
Okay.
Okay,
Okay.
for me it's okay.
Okay, Francesco, please share your screen and you can start your presentation
Of
on
course.
comparison of environmental benefits of warm or cold mix asphalt and its application in pavement layers, I think. Am I correct?
Yeah. Yeah.
Okay.
Uh, Give me 10 seconds to
Oh, yeah, yeah,
start.
yeah. Take your time. Take your time. No worries. We can wait.
Sorry.
We can wait. Don't worry.
Okay. I'm sharing the screen.
Yes.
Oh, right. Give me another. I have a little a problem with
Yes, yes.
with PowerPoint.
Francesco,
Give me
Francesco,
few seconds.
don't get anxious. We can wait, of course.
Thank you.
You're very welcome.
Maybe I'm ready. Okay,
All
now it's
right.
okay.
Great.
Okay, I will share the screen.
Yes.
Okay, can you see the screen?
Yes.
My share?
Yes, yes, we can say it.
We can see. Okay, so now I can start.
All right.
So, hello everyone. I'm Francesco Grazietti. I am PhD student at the University of Cagliari. My paper, in collaboration with James Rombi, Francesca Maltinti, and Mauro Coni, is titled Comparison of Environmental Benefits of Warm or Cold Mixed Asphalt and its application in pavement layers. The paper discusses the topic of using various asphalt mix technologies in road pavements, focusing on finding a sustainable solution to mitigate environmental impacts and promote the reuse of materials. So the essential points will be touched upon a presentation beyond a small introduction are HMA, so uh, hot mixed asphalt, warm mixed asphalt, and cold mixed asphalt. Definition, disadvantage, and advantage. Analysis of asphalt production and types across European countries. Asphalt production scenarios in Italy, energy analysis, and CO2 emission reduction. And in the final conclusions. So the road networks are the basis of most transportation infrastructure, critical for the movement of goods and people. To focus on the importance of roads, one must consider that in countries such as the United Kingdom, the European Union, the United States, and Italy, the road transport accounts for more than 88% of passenger travel in these regions. However, road infrastructure has a significant environmental cost, contributing to greenhouse gas emissions and climate change. Asphalt is one of the most widely used materials due to its versatility, durability, and strength. As I mentioned earlier, its production and application contributes to greenhouse gas emission and high energy consumption. This lead us to the development of new technologies, such as cold mixed asphalt and warm mixed asphalt, that can reduce this environmental impact. To this end, these technologies promote more efficient use of resources and reduce pollutant emissions. So let's define how the different types of mixer differ. HMA, hot mix asphalt, is mainly composed of aggregates, bituminous binders, and occasionally, depending on specific requirements, additive capable of modifying the final result are added. Processing temperatures, sorry, vary between 115 and 180 degrees for aggregates and 160 to sorry, and 160 to 175 degrees for the bitumen. HMA is valued for its high strength, durability, rapid laying process, and ability to be produced in large quantities, making it suitable for heavy traffic, extreme weather conditions. Warm mixed asphalt, or WMA, is so similar to HMA in composition, but use specific additives that allow it to be processed at lower temperatures. These agents are called viscosity reducing agents. The advantage of WMA to include energy savings, reduce emissions, improve processability, the ability to lay the pavement in colder weather, and faster opening of travel lanes due to shorter cooling periods. Key assessment to make is that the plant level is not require major modification to exist HMA production facilities, thus being able to be used immediately in maximum spread, sorry, over the territories. Despite these advantages, usually the physical and mechanical properties of WMA are inferior to those of HMA, and it does require additional cost because of the additive we need to use. Cold mix asphalt, or CMA, consists mainly, is the last one typology, consists mainly of aggregates and binder materials with water, solvents as additional components. The advantages of CMA, again, are reduced emissions, lower fuel consumption, better working condition for workers, and reduced road construction time. It increases the safety of operating personnel by reducing paving temperatures and inhalation of harmful substances. It's particularly suitable for small repair and for the construction work. Okay. Despite its advantage, CMA still does not achieve the strength and stability needed for high traffic roads. It suffers from moisture damage and require a longer curing time to reach full strength. So, a little comparison in the energy efficiency. HMA requires the most energy for production, while WMA consumes 15% less. CMA is most energy efficient as it does not require aggregate heating with an energy consumption of only 14 megajoule per tons, about 95% less than HMA and WMA. To produce the volume equivalent of 1 ton of lay material, HMA requires 680 of energy, while CMA and in situ chorus line consume 2/3 and 1/5. CMA requires significantly less energy for binder production than WMA and CMA. The case where the CMA started to the mixture is not taken in this study. It also does not require additional energy for production, unlike WMA and HMA. Regarding emissions, CMA has significantly lower emission during the production stage than WMA, obviously, and HMA. However, during the transport phase, CMA emissions are slightly higher due to the longer transport distance required for current CMI supplies, which are not so widespread now in the Europe territory. For the paving phase, the higher energy consumption is due to the more numerous pieces of the compactor roller over the material, but emissions are lower because the material is cold during the paving. An interesting zoom on European production comes from data provided by EPA, European Asphalt Pavement Association, in its 2021 report. The data show that Italian asphalt production increased significantly from 28 million tons in 2011 to 37 million tons in 2021. Germany maintained the highest production, more or less 40 million tons during the period. France showed stability, this time more or less 31, 35 million tons after an initial decline, while Spain experienced a substantial drop in production from 29 million tons in 2011 to 18 million tons in 2021. Great Britain experienced a growth in production from 22 million tons more or less to 25 million tons. Italy, despite having a less extensive road network than France, this is an example mainly for Italy. We use a lot of HMA and we produce more material in this period than France. This can probably be attributed to the need for extraordinary infrastructure maintenance and a change to technologies more suited to current standards, like draining pavement or higher mechanical performance needed. In alternative technology production, France stand out the most with a substantial growth in WMA production from 3 million tons to 6 million tons. WMA use in Italy is minimal, indicating an important opportunity to reduce environmental impact through this more sustainable technology. For CMA, France is also the largest producer, peaking at 2 million tons more or less in 2021, while Spain has seen a decline from 200,000 tons to 83,000 tons. Italy, on the other hand, has no data on CMA production, suggesting that its use is limited to partial repair of wear layers. This highlights how urgent is to continue to evaluate CMAs as an environmentally friendly solution through technological development and the advance of material technology. In the case, I in I have a little energy consumption saving in asphalt production, a little analysis. In the case of emission, various scenarios were also assumed for the Italian case. The data provided indicated the production of 1 ton of HMA and CMA results in emission of 53 and 36 kilograms of CO2. With the possible addition of 7 to CMA for the purpose of achieving higher mechanical performance can significantly increase CO2 emission to levels similar to those of HMA. Okay, this one? Okay, sorry. Among the various proposed scenarios, a gradual reduction in CO2 emission is observed as the percentage of WMA and CMA increase relative to HMA. The reduction for the emission is not so significant, going from 51 kilogram tons per tons in the first scenario to 48 kilogram per tons in the fourth scenario. This is due to the limited impact of WMA and CMA technologies on overall emission, the potential durability and strength limitation of CMA, and the possible increase in CO2 emission due to the addition of cement or additive to CMA. In the final, warm mixed asphalt and cold mixed asphalt offer substantial energy saving compared to the traditional hot mixed asphalt, obviously. Reduction in CO2 emission are minimal with WMA and CMA, highlighting the need for continued research to find new mix design, okay, capable of maintaining the required mechanical characteristic, but also reducing emissions. Sustainable asphalt production technologies are essential for responsible resource management and mitigating climate change impact. Emphasis on waste recovery and innovation in material development will be the key to creating a sustainable and environmentally friendly asphalt industry in this period. Okay, I've finished. Thank you, everyone.
Thank you very much.
Okay.
Do we have any questions? Sophia, do you have any questions on Francesco's study? Or
No.
should we proceed?
No.
Okay, okay. So next presentation is Sophia's presentation. Thank you very much, Francesco. Thank you very much. Sophia's study is entitled Towards an Urban Smart Mobility, Preliminary Results of an Experimental Investigation in Ariana.
Yes.
Artena, sorry, I'm sorry. Okay, Sophia, you can start. You can share your screen whenever you're ready.
Yes.
And we are eager to hear you.
Okay. Good morning, everyone. I'm Sofia Nardoianni. I will present the work entitled Towards an Urban Smart Mobility, Preliminary Results of an Experimental Investigation in Artena. Before starting, I want to thank my co-authors, Professors Mauro D'Apuzzo, Vittorio Nicolosi, and Stefano Puzzi, and engineers Giulio Evangelisti and Giuseppe Cappelli. In recent times, there have been more and more new impulses to rearrange European cities in a more intelligent way. The city of Athena has become the protagonist in hosting the national project Smart Urban Mobility Management or SUMMA as part of the Smart Italy project, with the aim of improving new digital technologies such as Internet of Things, artificial intelligence, technologies, blockchain, and the use of 5G communication networks to improve the competitiveness of transport. With the increasing number of movements from rural areas to cities, especially with an increasing in global population, several cities around the world have the ambition to become more sustainable and smarter. Recently, firstly with the Agenda 30 and its 70 UN Sustainable Development Goals for 2030, and secondly with the Next Generation EU in Europe, which give a great boost to tackling the problem of urban mobility, the problem of creating smart and sustainable cities is more critical than ever. To transform a city into a smart city, IoT technologies must be adopted, and this is possible today with digitization, with the implementation of the maximum performance of digital infrastructure, such as 5G, and the recent development and deployment of artificial intelligence and machine learning technologies for transport automation, the Intelligent Transport System, ITS. In this context, the project SUMMA is trying to implement new technologies, making use of modern digital technologies and 5G communication networks for the management of a transport system in a small city. The project focuses on application of an intelligent mobility paradigm based on a digital platform that employs advanced mobile broadband, the so-called machine-type communication, and mobile edge computing. The digital platform was designed to help AI algorithms for image recognition and interpretation of traffic field data selected by HD cameras. The system was used to evaluate the origin destination flow in real time. The estimated OD matrix, together with the collected traffic counts, can be used to develop and calibrate a travel demand forecasting model that will enable the assessment of urban mobility externalities. Preliminary results obtained on a test site located in the city of Athena seem to indicate that the proposed system is a promising encapsulating model of vehicular traffic. The application form used for this case study is the travel demand forecasting model that consists of 4 submodels by virtue of the characteristics listed above. It turns out to be a cascade model in which the data of input of the successive submodel are the data of output of the previous submodel. Such submodels are divided into emission model, distribution model, mode choice model, and path choice model. The supply model, however, consisting in the limitation of the study area, zoning, extraction of the base network, and the definition of the demand components. Having carried out the preliminary studies on the distribution of the population and the relative productive activities of Athena, an aggregation of the internet traffic zone is proposed equal to 11, compared to the microzoning proposed by ISTAT. To define the basic road network, the types of roads considered are state roads, municipal roads, and local roads. Having defined the network graph, it was possible to evaluate the origin destination matrices for different morning, afternoon, and evening peak times. Such matrices consider only the region study and work. Therefore, they have been amplified by 30% to include the reasons of the regions and by 10% for the presence of heavy vehicles. The proposed method for traffic detection is based on the use of the video monitoring system through the presence of cameras, which allow continuous protection of traffic scenarios that take place on a stretch or at a road crossing. Cameras with onboard artificial intelligence algorithms installed at strategic points in the city can recognize, classify, and count vehicles, monitor their movements, and detect their speed. In more detail, the latest generation cameras can extract precise data on vehicles, type, color, brand, license plate, direction, and so on. from the image and, according to the algorithm adopted, detect anomalies in their behavior, vehicles stopped or with wrong ends, and locate their movements within the city. In addition, they automatically detect traffic jams, accidents, abnormal events, and provide statistics on the temporal and real-time succession of traffic condition. Intelligent image processing allow you to send event notification and alert operators in real time. In addition, all the data collected by the cameras give a timely picture of urban mobility, resulting in the planning of efficient vehicular management. After analyzing the internal road network of the municipality of Artena and its external links, 7 strategic points were identified. 4 refer to perimeter area ABCD of the urban center, then detect traffic in or out of Artena to neighboring municipalities' external section. And 3 are organized internally to the municipality, EFG. The identification of these strategic points make it possible to optimally position the machine to be assigned. Once the location of the cameras had been defined, it was necessary to identify the traffic data they intercept, divided into trips to the municipality of Artena, trips from the municipality of Artena outwards, trips from the outside to the municipality of Artena, and transit trips. A post-processing algorithm has been developed and implemented to obtain relevant traffic information from the automatic detection camera network. The structure of the algorithm, by means of a schematic representation, is proposed in the 2 cases of stream intercepted by a camera on the section of the cordon and by a camera located in the inner urban area. For example, analyzing the zone to the cordon, if a vehicle is not detected in the next zone for chronological order, the destination of it will be an area inside the network and the trip will be of the type external-internal. If the vehicle is detected in one or more internal zones, then the destination will be an internal zone and therefore the trip will be external-internal. If instead the vehicle is detected in internal areas and in external one, then the destination will be an external zone and the trip will be of type external-external or road crossing. The same apply to inland areas. All this relevant traffic information has been reported within a single origin destination matrix, where travel within a single traffic zone, so-called intrazonal travel, has been neglected. The structure of this matrix provides information on the probability that a vehicle intercepted by internal cameras and those located in the external areas can reach a certain traffic area or another. All this is expressed in probabilistic terms, as the number of cameras is insufficient to cover the entire municipality of Artena. If this had been possible, the destination of a vehicle would have been identified in deterministic terms. The platform SUM has been implemented in a specific dashboard that allow to obtain the necessary data to carry out studies on the mobility of the municipality of Artena. This platform allows for a typical day and a user-defined time slot to obtain the estimated traffic counts from the cameras and derive the relevant OD matrix. This traffic data will then be implemented on development of a travel demand forecasting model by means of a macro modeling approach. In detail, OD estimates have been used as information basis for a macroscopic analysis to perform a traffic assignment and to calibrate a traffic forecasting model at urban level. To define the intervention measures aimed to improve the sustainability of the municipality of Artena in terms of mobility, the traffic model previously described has been developed. These figures show the vehicular flow from the origin destination matrix derived from ISTAT data. With the data elaborated by pre-mentioned Summa platform, several of the matrices have been obtained. Below are the results of a typical day in the morning time slot, a quarter past 10 to a quarter past 8, in terms of vehicular flow and saturation rate. As it can be easily detected by the analysis of the obtained results, road section connecting CD of Artena with the nearest municipalities are those affected by higher traffic flow compared to those pertaining to the internal roads of the municipality themselves. Following the assignment of traffic by means of the user equilibrium method, the model needs to be calibrated with traffic counts provided by the cameras. A comparison has been made between the calibration based on the OT matrix derived from community traffic provided by ISTAT within the census data collection activities, that is referring to the morning peak time, a quarter past 7 to a quarter past 8, and the calibration based on the estimated OD matrix obtained from the automatic detection cameras within the Summa platform. As it can be clearly highlighted by these preliminary results, the calibration of traffic prediction macroscopic model performed on the estimated OD matrix obtained from the Summa platform shows a better agreement between predicted and measured traffic flow than that obtained on the ISTAT matrix, exhibiting an higher coefficient of determination. It therefore seems that the proposed post-processing algorithm seems to better capture the mobility partner in the examined urban area. In conclusion, the trips of the territory of Artena were analyzed to carry out a study of the area and define the origin destination matrices that, together with the cost function attributed to the graph, allowed the construction of the network model. It was presented the structure of the digital platform that the Summa project aims to achieve in order to eliminate the numerous and costly manual traffic counts and develop mobility strategies. All this through a network of sensor AI cameras managed by a data analysis algorithm. The data obtained from the platform has been implemented in a macroscopic model of traffic forecasting, achieving results in terms of network saturation and traffic volume throughout the road network, even if it is not covered by automatic detection cameras. Comparing the calibration obtained from the OD matrix provided by ISTAT and OD matrix estimated by the proposed post-processing methodology within the Summa platform, the best results are obtained with the latter approach. Thank you for your attention.
Thank you very much, Sophia.
Thank you.
Do we have any questions?
No, for me it's all clear.
No, nothing.
Thank you.
Okay. Okay, thank you very much, both Francesco and Sophia. Unfortunately, we missed the other two presentations. So the participants never showed
Okay.
up. So I think that we should close the session. I will leave the room open in case someone shows up, but I really don't think so. So thank you very much, Sophia and Francesco, for
Thank you. Thank you to you.
participating, for
Thank
presenting
you.
your work. Thank you very much. Thank you.
Thank you.
Thank
Thank
Bye
you.
you.
bye.
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 Hello, can you hear me?
Yes. Hello.
Hello, Martina.
Hello.
I am Maria, your technical assistant, and
Okay.
you are the chair.
Yeah,
And I think that we can start in 5 or 6 minutes or so.
that's perfect. Thank you.
Okay, okay, thank you very much. Okay, Martina, can you hear me?
Yes.
Okay, I give you the floor so you can start whenever you want.
Okay.
Okay.
So today we are here. First of all, thank you for being here. We are here for the session on Metropolitan City Lab, and we have four contributions to present today. So I will start with the presentation of the two works. The first one is the minimum environmental criteria and climate issues in the metropolitan urban ecosystem. So I will share my screen.
Yes, please.
Just a second. Okay, do you see my screen? Yes, I didn't hear you.
Yes, we can see it.
Okay, perfect. So let's start. Hello everybody again. My name is Martina Sinatra, and this work was done with the collaboration of Professor Ginevra Balletto and Giuseppe Borroso. Minimum environmental criteria are the main environmental sustainability requirements for supply services in national and international public procurement. The main aim of the MAX is to promote the purchase of sustainable goods and services, thus contributing to the reduction of the environmental impact and the protection of natural resources. The adoptions of MAC by public authorities represents a strategic choice to promote the circular economy, reducing waste and greenhouse gas emissions, thus preserving at the same time the quality of the environment matrices. However, we can say that MACs have two important limitations. On the one hand, they can be interpreted as a minimum rather than a maximum requirement. So, consequently, their adoption cannot guarantee the maximum sustainability. However, the implementation, on the other hand, however, the implementation is difficult to control in reference to the territorial context. So the aim of this work was to evaluate a set of contextual environmental indicators to support the adoption of the MACs. In fact, the knowledge and the representation of the context constitute a fundamental action for recognizing local problems, which are also useful for understanding global issues. Furthermore, a question that guided our work was how can MACs contribute to adaptation to climate change within the relative territorial context? So this question guided all our research. The proposed method consists in a framework, as you can see in the slide, and consists in identifying a set of indicators that are able to represent the variation of the following phenomena, such as temperature, soil consumption, green areas, sustainable energy production, and greenhouse gas emissions. In particular, we have two representations. The temperature variation was represented by the means of spatial autocorrelation. Thus, I highlight the positive proximity relationships. Instead, the other ones were represented by spatial distribution. So we can say that spatial autocorrelation is was used as such as an instrument to analyze this phenomena of the temperature. In particular, local indicator of spatial association that we call LISA were considered useful for examining the phenomenon under observation, and in particular to analyze the behavior of certain data and variable in geographical space, taking in consideration the characteristics of geographical feature of autocorrelate in space. In fact, as Tobler said in his first law of geography, nearby things are more related than distant things. Consequently, area units can mutually influence each other in geographical terms and in terms of the data that are referred to such units. In particular, in this analysis, we use the local Moran's index, which allow to assessing for each location the similarity of each observation with its neighbor, and 5 combination can be obtained from its application. We have hotspots that are called hotspots, such as areas with high value of the phenomenon and high level of similarity with its surroundings, cold spots as areas with low values of the phenomenon and low level of similarity with its surroundings, and potential spatial outliers that's divided into categories with high values of the phenomenon and low level of similarity with surroundings, and low values of the phenomena and high level of similarity with its surroundings. The last one is the lack of significant autocorrelation. One of the interesting characteristics of LISA is providing an effective measure of the degree of relative spatial association between each territorial unit and its neighboring elements, thereby highlighting the type of spatial concentration and clustering. So in this work, we use different data sets. In particular, for temperature variation, the local climate change was chosen. And it's a data set created by the Copernicus Initiative and the European Center for Medium Range Weather Forecast, and contain estimates of temperatures measured at 2 meters above the ground with reference to a grid composed of cell 5.5 per 5.5 kilometers. For land take and green areas, we choose to use the Copernicus Urban Atlas, which provides a more defined and detailed classification on land cover and the land use, organized in terms of functional urban areas that we call FUA. For greenhouse gases emissions, the CO2 emissions were found on the National Institute of Statistics ISTAT database. So to test the methodology, we choose as a study area the metropolitan city of Cagliari, because it is an area that is of regional importance. It is an administrative intermediate unit established in Sardinia, and it consists of 17 municipalities and has a population of 420,000 inhabitants. The city of Cagliari is the capital of the autonomous region of Sardinia and of the metropolitan city, and it's an economical, political, and administrative center of Sardinia. The analysis was carried out considering the average annual temperature recorded over a time interval for 2006 to 2018, attributed to each municipality of the metropolitan city of Cagliari. These data were used as an input for the local moral index calculation, and the related map are shown. The analysis, as we can see, was conducted on the temperatures of 2006 and 2018. As we can see in the figures for municipality of Cagliari and Monserrato, we have an high spatial autocorrelation of temperatures for both years. For this reason, the focus were therefore on these two municipalities. The results of the evaluation of climate-city interaction for these two municipalities shows how there was an increment for the indicator discontinuous very low density urban fabric. Also, we, as I said before, we spatialize this data. This for the indicator land take, this for sustainable energy, again, sustainable energy, and greenhouse emissions. Also, the results suggest that it's necessary to adopt a policy that carefully considers social, economical, environmental impact in planning decision. So, in conclusion, we can say that CAM is an effective tool for both new construction and urban regeneration. The latter is to be preferred because it limits land use consumption to the protection of environmental sustainability. However, regardless of the type of intervention, urban complexity requires a consistent representation of the territorial context to ensure the consistent monitoring of max and promoting and ensuring sustainability through the process of the circular economy. In this sense, the work presented today constitutes a first contribution which will be the object of future developments with the implementation of the methodology through specific case studies. Thank you for your attention.
Excuse me, Vincenza, you have to shut your microphone down, please. Excuse me, Vincenza.
Sorry.
Okay.
Okay, so
I'm sorry.
that's no problem.
Okay.
Okay, I finished my first presentation, so I think we can start with the second one. And it's a work presented by Professor Ginevra Balletta, Martina Sinatra, Alessandra Milesi, Emilio Ghiani, and Giuseppe Borruso, and is entitled A Conceptual Framework to Correlate the Electricity Transition and Well-being and Equity in the Italy Case. So I will share again my screen. Okay. Here we go. So, as I said, this work is entitled "A Conceptual Framework to Correlate the Electric Transition and Well-being and Equity, the Italy Case." The macroeconomic indicator of energy efficiency represents the energy performance in spatial terms, or the amount of energy used to produce a given unit of gross domestic product. However, the electric transition draws attention to the need to pursue combined sustainable objectives, both economical and environmental well-being. Through the intermediate spatial dimension metropolitan city province, currently the most coherent to represent and support a just an energy transition. In this work, we intend to develop a methodological approach for the comparative evaluation between electricity energy consumption and the recent equitable and sustainable well-being indicators. In this framework, the aim of this work is the spatial representation of the electricity transition phenomenon in Italy. In particular, the spatial autocorrelation with an intermediate territorial basis is taken in pre- and post-COVID period. Between and the analysis was carried out between electricity consumption and a selected series of best indicators to recognize spatial equity and to recognize spatial equity. So, what are best? They are the best for more than 50 years. We can say that there has been an international debate on the so-called surpassing GDP. as only a measure of well-being. This is nourished by the consciousness that the parameters on which to evaluate the progress of a society cannot be exclusively economic, but also address the fundamental social and environmental dimension of well-being, together with the measure of inequality and sustainability. The best indicators arose in 2010 in Italy to assess equitable and sustainable well-being, with the purpose to evaluate the progress of the society not only from the economic point of view, but also from the social and environmental side. In particular, traditional economic indicators have been implemented by measures concerning people's quality of life and environmental issues. But these indicators have been included in the process of the Italian government economic planning documents. So this is innovation seeks to integrate economic measure in order to take account of other dimensions of the societies. As we said, the well-being and environmental sustainability. Recently, best indicators have been linked to indicators for monitoring the 2030 agenda for sustainable development targets. So in this work, we choose 4 indicators. 2 for electric transition, as we can see in the slide. In the slide are electric energy consumption, electricity from renewable sources. And two for equitable and sustainable well-being, employment rate, and life expectancies at 65 years old. These data were represented by autocorrelation because we think that energy well-being relation can be examined by these means. In particular, a spatial autocorrelation can be applied on data or indicator referred to a set of contiguous geographical units as administrative units, and it can be useful for evaluating local effects and clusters in terms of attribute and geographical data. Spatial proximity, in fact, can influence phenomena under a phenomenon called spatial autocorrelation, as we said. Data can be mutually influenced, but both in terms of geographical shape and proximity in terms of the attribute values attributed to such units. By analyzing spatial autocorrelation, it is possible, as we said before, to observe a variable behaves with reference to its location in space and with reference to what happens in its proximity. In this work too, we choose to use the local moral index to perform our analysis, which allows us assessing for each location the similarity of each observation with its neighbor. As we said before, we from its application, it is possible to obtain 5 combinations that are not significant. We have no significant autocorrelation values detected. We have high values of the phenomenon and high level of similarity with nearby areas, known as hotspots. Which means low values of the phenomenon and low levels of similarity with the nearby areas that are called spots. Or we can have low high. Low high, we have low values of the phenomenon and high level of similarity with the nearby units. And the last one, high glow, we have high values of the phenomenon and low level of similarity with the nearby areas. These two, low high and high low, they are called, as we said before, potential outliers. The case study chosen was the area, the Italian territory. Italy is a peninsula located in the southern part of the European continent, and the climate is mostly temperate and characterized by dry and warm summers in coastal and southern areas, including Iceland. Instead, in the Maya mountains chains, there is a prevalence of a cold climate, characterized by no dry seasons and no cold or hot summers. From the administrative point of view, it's organized in 20 regions, split into 107 provinces. So, in this work, the analysis, as we said before, was performed by considering a set of indicators assigned to each Italian region and province, and they refer to the interval 2017-2021. These data were used as an input to calculate LISA, and in particular, as we said, the local Morans index. It is important to highlight that in order to achieve spatial proximity for the application of the method, some simplification have been adapted in the spatialization of Iceland at regional level. On the one hand, Sicily has been united to Calabria to make it contiguous with Italian territory, and on the other hand, Sardinia has been excluded and inserted after elaboration due to its distance from the other Italian regions. So, as we can see, the analysis was performed on regional data for years 2017 and 2021, while on provincial data for 2021 only, because as we can see, the energy consumption indicator it was also available for 2017. The application of the method to the sets of these indicators in the regional and provincial dimension yielded the following result. The first, we can see that electricity consumption in Italy is influenced by various factors, including the physical geographical conformation with different meteorological conditions, as well as the organization distribution of economic productive activities. The LISA elaboration, based on the regional and provincial dimension, confirm that northern Italy is characterized by an high autocorrelation of electricity consumption. In confirm that northern Italy is, in particular, shows how the region with high autocorrelation of electricity consumption are located in Lombardy, Emilia-Romagna, and Veneto, and are characterized by a climate with more extreme temperatures in winter and summer. But above all, they are characterized by an high gross domestic product. The other figures of the province analysis shows how high autocorrelation respectively affects provinces of Bergamo, Cremona, Mantova, Monza, Trento, Varese, and Verona. That are distributed on the border between the region Lombardy, Emilia-Romagna, and Veneto, which we have said are also characterized by a significant investment in cohesion policies. So these are the other results that we have. The other results for electricity from renewable sources, employment rate, life expectancies at age of 765. In conclusion, to achieve the so-called carbon neutrality by 2050, the main tool is represented by the energy transition, we can say, with the transition from an energy mix centered on fossil fuels to one with low or zero carbon emission, based on renewable sources. A great contribution to decarbonization will come from the electrification of consumption, replacing the electricity produced from, as we said, fossil sources with the generated from renewable sources, which also make other sectors cleaner, such as transport, and from the digitalization of network, which improves energy efficiency. The energy transition, however, is not limited to the progressive shutting down of coal-fired plants and the development of clean energy. This is a paradigm shift of the entire structure of energy production and the utilization, for example, for a transition based on spatial equity, with benefits not only from the climate but also for the economy and community. Thank you for your attention. Okay.
Okay, so any questions or should we proceed? Any questions on Martina's presentations? Nothing?
Nothing.
Okay, Martina, since you are the chair, okay,
Yeah.
you have the floor.
Yeah.
Okay.
Okay. So we have the next presentation from Vaclav Skala. Sorry for my pronunciation. Tristan Belot and Xavier Berol. Wavelength of consumption from RGB. Who will present? There's someone who will present. Hmm, I think there's no one.
Okay, we can proceed to
We
the
can
next
proceed.
one.
Yes. So the next one is a work from Ayman Al-Kabaji, Faisal, sorry for my pronunciation again, Ben Sali and Sarada Prazada Dakwa, a close-up on the AI radiologist software. Who will present? Okay.
Hello there, how are you?
Hello? Hello?
Hello.
Okay, let me share my screen just a moment, please.
Yes.
Okay, share. Okay.
I think he accidentally left the room.
I think so.
Okay, so we can wait a bit.
Yes, that's not a problem.
Okay.
Hello.
Hello.
Hello again.
I sincerely apologize for the
It's
technical
not a
issues that I'm
problem.
having. I, I closed one program and everything, all hell break loose.
It's not a problem.
Okay. Okay. Let me share again my screen.
Yes.
Okay, can you see it?
I cannot, but okay.
We
Now,
can see your screen. Yeah.
Okay, now do you see the presentation?
Yes.
yes.
Great.
Okay, perfect. Okay, so hello everyone. Thank you for having me and for accepting our paper. So our paper is related to machine learning and AI. So we are focusing on it. The paper itself focuses on the AI radiologist software that we have made, but that doesn't mean that we will not discuss the basis of machine learning that we have used. So my name is Ayman El Kababji. I'm presenting on behalf of my co-authors, my professor Faisal bin Siali from Qatar University, and Sarada Prasad Dakwa. He's a doctor in Hamad Medical Corporation in Qatar. So the outline for this presentation is as following. So we will start with the problem statement, then we will proceed with the methodology that we have followed, along with the results and discussions that we have noticed. Then we will be concluding and mentioning our future work. And in case if you have any questions, the floor is yours. So what is the problem statement that what are we trying to solve? So basically, 2 million people around the world globally and annually they die because of liver-related diseases. Half of them are related to cirrhosis, and the other half are related to hepatitis and hepatocellular carcinoma. So they are types of cancers. Also, it is a hub for metastasis, like where the cancer cells come from other organs, but it goes to the liver, such as colon, rectum, etc. Also, they are usually the liver and its lesions are usually analyzed when there are tumor that was detected, so that you can stage at what stage it is. So, what is the aim of our project? Really, it's to delineate the liver, tumors, and vessels within the liver, such that we can provide a 3D accurate object of that liver. So what is the, just to show how it looks like visually, so what we will be taking as an input is the CT scan, and then our output it will go through the AI radiologist software, and then hopefully what we will be having is the 3D object of the liver, such that the clinicians or surgeons can see it in front of them before doing the procedure, such as hepatectomy, for example. So our system is as following. We have the CT scanner. Our input is CT scans. Then we have once the scan has been done, then a clinician will input the clinician will input the data to our software, where there will be some data processing done on the data first, and then we will apply artificial intelligence on it, and such that then we can have the holistic liver tissue delineation, as I've shown you in the previous slide. Now, I will mention briefly the pre-processing steps that we have done along with the machine learning environment. So first of all, we have started with data collection to train our models, and we have so all of those investigated all of those data sets, and the one that was suitable for us was the MSDC TA. So MSDC stands for Medical Segmentation Decathlon Challenge. And T8 stands for Task 8, which is called hepatic vessel on their website. Why we chose this is because it has around 440 CT records, and we have the liver segmentation and the tumor and vessel segmentation for them as well. So it's the largest available segmentation. Although it's worth noting that the liver segmentation was not provided by the challenge providers; it was provided by third-party researchers, and we are citing them. Then after the data collection, after we confirmed that we will be using this data set, we went for data pre-processing. So what we did is that instead of working with the whole volume in 512 by 512 dimensions, we rescale it down to 256 in both dimensions. We do some volumetric rotations just to make sure all of the volumes are facing towards the same direction. So if one is facing upwards, then we rotate it to right. Then we do some contrast enhancing. We also do some standardization to make sure, because the CT scans come from different standards and different machines, so we needed to do that standardization. Also, we did some dataset normalization to ensure that the machine learning algorithm will converge quickly, and then we slice the volume into slices. So in the sense that we prepare the data to inject it as slices into the model. Now, after that, we tried different machine learning algorithms like unit, res unit, dense unit, etc., with different initializers, different optimizers, and we tried loss functions. The best one was the BCE for our case, and we had all of those evaluation metrics to check if our model was performing well. This is how this is the what really happens under the hood. So once the input CT scan is inserted, then it will enter the liver segmentation convolutional neural network. Once it's entered, then the output of it will be multiplied. The mask output of this liver segmentation convnet will be multiplied by the input to the lesion segmentation convnet and the vessel segmentation convnet. And then after the output of the three, then they will be combined into a single 3D model. And for the interpolation, we are using an algorithm provided by the SciPy library called Martian cubes. So if you give it 2D slices, it will generate the 3D object for you. And this is the convnet we are using. We are using the unit convnet. Yeah, it's quite famous, so I don't think we will have to spend much time on this one. These are, as I mentioned, the data sets that I mentioned before. Out of all of those, as I mentioned, the MSDC has around 440 records. 303 are for training, 140 for testing, and it's really the biggest one of them all. So we ended up using it. As I mentioned before, what we would like to have at the end of our application is a 3D model, and that 3D model basically it has different elements. So we end up with an .obj file and .mtl file, and with the .obj file, what it has inside of it, it has three types of vertices. Which is V1, which is the geolocation, okay? VT1 and VN1, these are things that we don't use. They are optional. They are there, but we don't really use. On top of my head, I forgot what they do exactly. They are more related to the texture, which is not something really relevant for us. And then you have this component, which is the F. F means the face. So here, F here, if we take 1, 2, 3, what it will do is that it will take vertex 1, vertex 2, and vertex 3, and because 1, 2, and 3, and what will it do is that it will make a triangle face out of those three vertices. So this is how an .obj file works. So in the end, what we do is that we combine all of the tissues that we segmented with our machine learning algorithm, the parenchyma, so the liver itself, the tumor, and the vessel, and we put them inside a single .obj file. So you can see here, first of all, this is an MTL file. MTL file, what it does is that it defines the material that will be used with the objects. So here we are telling it the parenchyma, give it this specific color. Tumor, give it this specific color. vessel, give it that specific color. And then in the .obj file, what we do before the faces related to parenchyma, we insert it here. We insert this material, as you can see here, parenchyma. Then before the faces of tumor, we use the tumor material, and then before the faces of vessel, we use the material vessel. So after, without going into all the details that we have done to get the machine learning, the best machine learning models, we ended up with those three for the segmentation of liver, tumors, and vessels. So there is like maybe more than 30 different runs with different hyperparameters that we did, such that we obtained those results. So here, you can see here for the tissue we are trying to segment is the liver. We have used the reduce LR on plateau scheduler. We started with this learning rate, and we achieved this performance. So 89% on DICE, 96% on intersect over union. Then we have here the relative volumetric distance, average symmetric surface distance, root mean square distance, Hausdorff distance, and so on. So all of those just evaluate the performance of our model. And for the liver segmentation, our model is performing extremely well. For the tumors and vessels, they are within the range of a state of the art, but of course they could be better. And you can see here some results related to the how our performance. So this is the original CT scan for two different CT scans, slice 90, slice 83 for 294. Then you have slice CT scan 268, both slices 27 and 20. And here you can see this is the ground truth, and this is our segmentation. So you can see it's doing quite well in this segmentation task. Here, just to show you the ground truth and our segmentation, and to what extent it's actually similar. So you can see that the liver segmentation is extremely well. Vessel segmentation is capturing the main picture. Tumor segmentation, when the tumor is large enough, it detects it properly. When it is small, sometimes it could miss it. Similarly here, another case. This is on the left is the ground truth, on the right is our segmentation. And this is and then here we come to the crux of the paper. Here we focus on the AI radiologist. This video shows you how the AI radiologist application that we have created can be used. So this is a video that shows you how it's being exactly used. So here we load the volumes that we want to segment, okay? And after we load the volumes, then here we select the models that have been trained, that I've mentioned to you before. Now, once those two things are imported, then that's it. Application takes everything. It's now up to the application to generate the outputs. You can see here below that it gives you a status where currently the application is at in terms of generating the masks. Now, currently it's residing at the vessels. Now, you can see here now it created the complete model object. Now, once you open it with any application, really, the 3D viewer from Microsoft, you can see that you can open it, and it's quite neat. Now, the other object, this object doesn't take a lot of time. Why? Because it doesn't have a lot of slices. And if you remember the images from before, you could see that it is more pixelated or voxelated in this case, because we are working with 3D. The first liver was more voxelated because the distance between each slice and another is bigger. Here we also and in the other case, this volume is bigger, so the slices are a lot more. So the distance is less between each slice, so it has a better resolution. And we also have with the application, we show the instructions on how to use it and the about us if someone would like to get in contact with us. So and they can ask us questions. They are more than welcome to. Just a second until it finishes. Okay, it's almost there. Now it's combining everything into a single file. Yep. And if you notice, it's done sequentially, so you don't have to wait for all of the volumes to be done to inspect them. You can inspect them one by one, so that if you have multiple volumes you would like to check, you don't have to wait for everything. And here you can see how this has more resolution into it. Why? Because it has more slices, and the distance between each slice is different, is smaller. Just to describe what I mean here. See here that the slices are far from each other, so it looks like it's cubes. But here, because it's the slices are very adjacent to each other, so the physical distance is smaller, then you don't see that effect. And the also with the model itself, with the 3D model, we also generate the masks, so they can be opened with any kind of software that is accepts this extension, which is the zip file. And yeah, that's about it. So what we conclude from this paper that we have done is that we close the gap between the medical academia and the industry by creating this application. So because sometimes researchers, what they do is that they create the models, but it's not easy to deploy them in clinical scenarios or in other scenarios, not even related to medical. So in that sense, we try to close the gap with an application that is pretty straightforward to use, and doesn't have a huge learning curve. Also, we created a multi-object 3D interpolation of the segmented masks, because you have each one in a 2D mask by itself, but then you would want to see the whole picture when all of them are together. And related with the liver segmentation task, we surpassed the state-of-the-art results. For the future work, we would like to make the software compatible with DICOM images format, also further enhance the results for tumor and vessel segmentation, and maybe perhaps if we have more time, extend the segmentation to other human organs. Thank you for listening. If you have any questions, please go ahead.
Thank you. Are there any questions? I think there aren't. So I don't know if we can move to the other presentation. If someone will present wavelength computation from RGB. I don't see anyone here. So I don't know if we can wait or we have to end the session.
Martina, it's up to you.
Okay.
Since you're the chair, so you decide.
Okay. So I don't think they will connect soon. So I think we can stop the session. And I thank you for participating to ICCSA 2023. And it was a pleasure to hear your presentation.
Thank you. Likewise.
Thank you.
Thank you very much. Thank you all for your presentations.
Thank you for your help.
Okay.
Oh, wait.
Okay. Yes. Yes.
Hello, Professor Baruza.
Hello.
Do you want to say something?
Thank you very much for
We cannot hear you well.
Thank you for your sharing this session, and
Thank you
everybody of you for the presentation. Thank you.
Thank you for choosing me.
Bye.
Thank you.
Bye.
Thank you very much. Bye
Bye-bye.
bye.
Ciao.
Bye.
Bye bye.
Sorry, I have to do something to validate the session.
No, you just leave the room, and I will send you an evaluation form later.
Perfect.
Okay.
Perfect. Thank you
Bye
so
bye.
much.
Bye bye.
Bye.